Thank you, Chiara, for the warm welcome. So today we're going to talk about compile time deadlock detection in Rust using Petri nets. Let's first have a look at the tool itself I coded. So from a bird's eye perspective, the tool is a translator that converts the Rust source code into a Petri net model, which is a graph. And this Petri net model is then fed into a model checker that verifies exhaustively if the Petri net can come to a deadlock. And this is the output that the program generates. So I'm using internals of the compiler, accessing the crates that the rustc compiler uses to traverse an internal representation of the compiler and then translate that. So the compiler in this case is a dependency, and the model checker is also a dependency. But first, let's look at what Petri nets are. So Petri nets are a nice mathematical modeling tool that can be used to describe and analyze concurrent systems. It looks like a graph. It has places and transitions. The places are the round nodes you see, and the transitions are represented usually with rectangles. And usually, I mean, it would be nice to have some kind of animation here of the thing. Let me check if this works. So basically, when they get animated, let me check if this works. We're having demo issues. So you see that the thing moves, right? This is a GIF. So when the transitions fire, they consume one token from the place that points to the transition, and they generate the token on the other side in the place. So the transitions, we'll see how when they fire. But the goal is that you see how the token flows in a cycle through the network, and this is what allows you to model concurrency, because the transitions fire in a non-deterministic way. We don't know which transition can fire, but they must be enabled. Enable means that you have the condition that the places that point to the transition have a token in them. The same number of tokens as the edges you have from the place to the transition. So in this example, we see that transition 1 is enabled at first at the top, and then you can this transition 1 can fire, and it generates the 2 tokens at place 2 and place 3. And now transition 2 is enabled. If there were several transitions that were enabled at the same time, then we wouldn't know which one fires first. The point is that they fire in a non-deterministic way, and this allows us to model concurrency. So what can we model with this? First of all, we can model finite state machines. This is a simple coffee vending machine, and you can see that the token can flow from one place to the next, and depending on the coins you insert, you will eventually get back to the €0 place, or you can also get the €4 coffee at the bottom. But we can do much more than this. We can also model fork and join. We can model concurrent tasks, and this is basically how we're going to model like separate threads. So each thread is going to be one token, and the token represents the program counter, the instruction counter of that thread, and then we will spawn a new token so that we have a second thread, and that thread will then run the task. And the idea here is that at the right, the join transition can only fire if the 2 tasks are finished, and this models how a join behaves in practice. We can also do communication protocols. This is a simple send with acknowledgement. So this could be a nice model for a channel in the Rust standard library. If we would be able to translate the send and receive calls, we could then have this kind of Petri model, and we would use the model checker to then check if a deadlock can occur or not. So how does it work that Petri nets can tell us something about deadlocks? So there is something called reachability analysis, and Petri nets can be analyzed using formal methods to conclude whether the nets reach a deadlock or not. There is a similar, an analogous notion of liveness in Petri nets that's analogous to the the notion of liveness in computer programs. And the idea is that if you have a transition if you have no transition that can fire, then the net is dead. You cannot do anything. Like, you cannot move tokens, you cannot fire anything, and that's called a dead net. And the model checker can figure out if by firing transitions in a different sequence, you can reach that state. And the nice thing is that there are several model checkers that are being developed, and there is even a model checking contest that takes place every year. And these model checkers can handle quite big nets already, and much more complex than the kind of things that you get when translating a source code. So we can put these model checkers to use, and basically we just need the translation. We need to translate from the world of Rust source code to a Petri net, and from there the model checker takes care of the rest. And this idea of translating source code to a Petri net has been done before, especially for C, and it has also been done for Rust for simple mutexes. So the challenge, let's say, lies in supporting more synchronization primitives and adding more features, being able to translate more of Rust to Petri nets so that you can then analyze the corresponding Petri net. So let's now see how the translation itself works. So the compilation in rustc has different stages, different internal representations that are used through the process. First, we have lexing and parsing, converting the tokens, building the abstract syntax tree. Then we have the high-level intermediate representation. We go to simpler and simpler versions of the Rust programming language. And finally, we get to the code generation part when rustc generates the LLVM intermediate representation, and LLVM takes it from there and generates the executable. For this tool, the important part was selecting an intermediate representation that was architecture independent, but which was at the same time the lowest possible. So I wanted to have as many safety features from Rust already performed, that I didn't have to borrow check or replace types, or everything is done by the time you reach the MIR, the mid-level intermediate representation, and you don't need to do these checks yourself. It's like the simplest representation that's still architecture independent. And in this, by the time you get to the MIR, you already have borrow checker, type inference, and a lot of nice things that you don't need to handle yourself. And it's a simpler representation, so that makes the translation also simpler. So how does it look like? MIR looks like this. You have functions, just functions. Closures are also functions. And these have basic blocks, and the basic blocks consist of statements, and at the end they have a terminator statement, which is the only place in which the control flow can jump from one basic block to the other. So basically in your function, you start at basic block 0, you do some things, you jump from one block to the other, and eventually you get a block like here, the basic block 2, and you return. So, and here you have like a terminator statement that has a function call, and here there's also a function call, but you have other types of terminator statements like calculating discriminants, which would be like ifs, or also like panics and things like that. And the nice thing is that this thing here can be represented as a graph. The graph looks like this. Every basic block gets translated to a block. So every basic block is like a node in the graph, and then the statement tells us in which direction we go. Either we go to basic block 2 if the function if everything goes right, or we go to another direction in case the function has a problem. So this can be translated to a graph. So you see that in the end, MIR is a form of a control flow graph that's used in compilers in general, is part of the theory, and this graph is then easy to translate to a Petri net, because you have the nodes that are the basic blocks are the places, and then you just need to put a transition in between, and everything is a transition in between, and you get a Petri net like we saw before. So first, let's look at like an example, a simple program that spawns a thread and just joins it. So the thread spawn should create a second token to model that thread, and the joining thread should wait for the two threads to finish before continuing. How does it look like? So we have here the result of the translation. We have the program start, the token, we put it there, and then we have the call to spawn. All the functions from the standard library are just modeled as a single transition. And I call the thread, the new thread goes to the left, and the main thread just continues on the right. And when the two threads reach this point, the token is here and the other token is here, then we can fire the join and the program finishes. In this case, there is no panic, so the program panic is not connected. And we can now model a mutex as very simple deadlock in this case, because not everything fits on a slide. We can lock a mutex twice and see, okay, why it doesn't work. So the program starts here. We create the mutex, then we lock the mutex the first time, and the mutex is just modeled as a single place. When you lock the mutex, you take the token from here. So the first time this can fire, and you get the token here. But then this transition will never be able to fire because you took the token from here, and then this is the net is dead. You cannot do anything. And when you translate this kind of thing, you need to be careful that at some terminator statements called drop, you drop the mutex guard, and that's when the mutex is unlocked. So you need to put the arrow that generates back the token here to unlock the mutex. So if you feed this, the whole net, to the model checker, the model checker will tell you, oh yeah, there is a deadlock, and you need to fire these transitions, this, and then you reach the deadlock. So you get a witness path. You get like the specific sequence of transitions that will lead to the deadlock, and you could use this to debug the program. Let's look at a more complicated case now, the condition variable. The condition variable is a more complicated model. I'm modeling the variable itself, which you're checking with the condition variable, and the convar itself. So let's have a look at it. It's not that difficult once you understand the idea. The idea is that you need to go from input to output, and there are two ways. If the condition is set and there is a token here, you can skip the wait, and you just go from input to output, and the arrow here regenerates the token, so you can go again you can again do the same thing from input to output. If the condition is not set, then you need to go through all this block on the right. The wait start fires if there is a token here, and you unlock the mutex. And here's where you unlock it. You lock it again by taking this. And the idea is that if you already called wait start, there is no token here in wait enable, and eventually someone will set a token here in notify. So then notify received can fire, can consume the token from the mutex and notify and go to the output. This is the happy path. If instead you didn't call wait, but you call notify, the lost signal transition here can fire, consume you the token in notify, and set again the token in wait enabled. This is a lost signal. So by using this model, I can detect lost signals in the Rust source code. We can have a look at a very small program, also for representation reasons. We will lock the condition, we will call notify with the same thread, and yeah, it will not work, of course. So here's how the net looks like. You get to the point here when you call notify me. In notify me, you will set the notify place here, but this will fire, will consume it, and you will never get to wait start here with also so this will fire, but the notify was already consumed. The token in notify was already consumed, so you will have a dead signal, a lost signal, and the model checker will be able to detect this. And what are the pros and cons of this approach? Like, first of all, well, there are some limitations related to the tool itself. I'm just one person. I worked on this for like full-time for 6 months, but I haven't been able to translate everything from the Rust language. Like, everything you can write in Rust has a mere representation, even if it's simpler, and you need to be able to translate everything that's possible in mir or in Rust. So yeah, I don't support closures, I don't support arrays, vec, but I do support like passing variables, structs, implementation, impl blocks. Then if you want to support other synchronization primitives like channels, read-write locks, barrier, you need to come up with the corresponding PetriNet model and, you know, track the variables in the source code, making sure that, okay, I have this mutex here, this mutex is this one here, so I need to connect to create the corresponding edge and, you know, construct a model, and then you support the feature. But this is a matter of time. This is something like, okay, somebody has to sit down and write the code, and you could make it work. I think I haven't checked everything, like also async and, you know, mutexes in async. That could get difficult. But for now, I haven't reached the limit. And then there is the question of, okay, what about the approach itself, not the specific implementation of the tool? So first of all, you have the state explosion problem. The number of states in the program grows exponentially, grows very fast. We have good model checkers. They keep improving, but maybe for a really big enterprise application, this will not be enough. And then there are also deadlocks that can be captured by this approach, because I'm not modeling the memory. I'm not modeling what specific value is in a variable at any given time. I just look at the structure of the program and translate it to a graph, and the model checker is able to figure a lot of deadlocks just from that. But if your deadlock depends on user input, or if you are loading code dynamically or doing something special, then of course it's not going to work. And also you have the case that, yeah, you need to draw the line somewhere. You need to decide, okay, what do I translate? What do I not translate? So for instance, I decided to draw the line in not translating libraries or crates you call, or translating inside of std or core, or, you know, syscalls. So eventually you need to stop and say, okay, I assume the outer parts do not have a deadlock. Let's just check this part, my system. I translate this, and I see what I can find. But there are also some nice pros. The nice pros is that it's a graphical approach, and the model is kind of easier to debug. This is no like complicated algebraic formula language. I think it's easier to understand. And there is like a clear correspondence between the control flow in the Rust program and the PetriNet. And you also get the nice thing that the model checker provides you with the sequence of firings that leads to the deadlock. So eventually you could build, I don't know, if you get creative, you could build some kind of tool that integrates that into the IDE and give you feedback. And you could, you know, interpret this as some kind of additional compile time check before running the program. So the idea would be to have a cargo plugin. The current implementation is a cargo plugin already, and you could detect more bugs at compile time before running your program. This could already figure out some complicated deadlocks when you have lots of mutexes or lots of condition variables, which maybe to a human it's difficult to grasp where the deadlock is, but for the model checker it's trivial. So this is the nice thing. Let's have a quick demo of how it looks like. It's so here I have the repo from GitHub, cargo check deadlock, crate published on crates.io. And I have a simple program called Dining Philosophers with structs. I have like different philosophers, the forks, and so on. This is one of the limitations. I cannot write for loops that have an index and, you know, create the forks and the philosophers in a loop, because I don't know which specific value of the I variable in the loop I'm passing into each philosopher. So this shows us an example. Okay, what can you not translate? You know, or if you start threads in a closure and you do like map and you pass the thing they need to execute, that kind of approach won't be able to be translated correctly. But let's say you wrote a program like this, and you want to figure out how to find a deadlock. So you just run the plugin with the source code, and you decide, okay, I want an output folder, and and I want like the witness path here with an additional argument. And the result is in the demo, you have the witness path, the specific sequence of transition firings that will lead to the deadlock. And and here is the representation of the net in the format that the model checker uses. Right now, I support only a model checker called Lola, Low-Level Petri Net Analyzer from the University of Rostock in Germany. But there are other model checkers that interpret a format called PNML, PetriNet Modeling Language, which is based on XML. And I can also generate those. So basically, I have other formats. I have 3 formats in total, PNML and also DOT for GraphViz. So for the dot representation, that's what you see on the slides. So this would allow you to quickly debug the thing. You can go online or construct the image, the SVG image from this, and then debug it. And then you have the PetriNet model representation. The nice thing is just by generating this, you could support other model checkers. You just need to find them, and it's like a pluggable backend. You just need another model checker. You need to output the PetriNet in the format the model checker supports, and you're good to go. So that's for the demo. And yeah, some links in case you're interested in the papers where this has been tried before. Here there are some simulators for PetriNets in case you're interested and want to play around with them. And that's it.